Hello, and welcome to Let's Talk, a podcast series by the Electrochemical Safety Research Institute, ESRI, at UL Research Institute. In the Let's Talk series, we talk to experts and scientists in the fields of energy storage systems, safety science, and standards, and learn about their experiences and perspectives. I'm your host, Taina, and our guest in this episode is Professor Anna Stefanopoulou. She is the William Clay Ford Professor of Technology at the Mechanical Engineering Department of University of Michigan. I will talk to her about her work in understanding and predicting battery degradation, as well as battery failures through a combination of experiments, physics-based modeling, control theory, and data analytics. Anna joined University of Michigan in 2000 after working at the University of California at Santa Barbara. She has also worked in the automotive industry, where she developed algorithms and calibrations for highly efficient and advanced powertrains. Her innovation in powertrain control technology has won her multiple awards and has been documented in a book, in 21 US patents, and 400 publications on estimation and multivariable control of dynamic electrochemical and thermomechanical processes in engines, fuel cells, and batteries. To help inform policymakers, she has co-authored 2 influential reports sponsored by the National Academies on the cost-effectiveness of fuel-efficient technologies for light-duty vehicles. Anna is also a fellow of the ASME, IEEE, and SAE. Anna, welcome to our podcast, and thank you so much for being here.
Good to be here. Thank you very much for inviting me. Very excited about it.
So Anna, you have a very impressive background working in varied fields, ranging from internal combustion engines to fuel cells and batteries. So could you tell us about your professional journey and how you became interested in working with lithium-ion batteries?
Oh, yeah. Wow, that's a long journey. Okay, so I will start in my diploma thesis back in Greece. I worked on large diesel engines and turbocharging them, and the emissions and fuel efficiency, of course, for the ones that they're marine engines. In my PhD thesis, I worked on automotive engines and vehicle engines, specifically variable valve timing. That was the best thing back then. I won't tell you when. But then later on, when I worked in industry, in the automotive industry, I actually worked on cylinder deactivation. And then in my first academic years as a professor, I worked in a lot of other interesting technologies that goes in internal combustion engines. Then, we developed more technology. We made the engines more efficient. I also became well known in some sense, and I participated in a National Academies committee where we looked at the cost effectiveness of internal combustion engines and the fuel economy of the cost effectiveness of the fuel economy of internal combustion engines. And that's when I realized that, that curve is going up as year progresses, and we're trying to tighten emissions and fuel efficiency. And at the same time, battery technology cost effectiveness was indeed improving at a rate where I could start seeing some balancing and some serious competition. And that is when I decided to be adventurous. I had also, of course, tenure, like some of us academics worry about. And that's when I jumped in learning myself, using my sabbatical to learn about batteries and working with 2 of my senior students that they really wanted to do something new. And that's when I got started in batteries, and I started in 2004, so almost 20 years ago, doing battery management systems specifically. So I'm in the controls and battery management field.
That's a very impressive journey. Thank you. So in your current research, you have studied the aging of lithium-ion cells and batteries, and more specifically, the modeling and prediction of battery performance degradation. Could you describe what your group is doing in this area? and share your perspective on why it is important to understand and model cell and battery degradation.
Yeah, thank you. Thank you. Indeed, the last decade or so, I have been working on degradation, and specifically the very hard problem of tracking degradation and aging with field data that come from onboard diagnostic systems in vehicles or in grid applications. Occasionally also satellites. But anyway, so that is a hard problem on its own for many reasons, including irregularity of use, but also because we don't know very well how batteries age. We don't have the full understanding of the evolution and the interconnection and the interaction between various degradation mechanisms and how they appear, how they get to actually affect the two things we care about, which is capacity loss, capacity fade, which results in lower range, and increase in resistance that causes power fade. So that is what I focused on. And because my background is controls, automation, of course, I started with more data-driven approaches. Like, can we basically take data from the field and look at the pattern and the trend and extrapolate? And as I became wiser and more adventurous, and I got brilliant students around me, a nice laboratory, I basically understood that data-driven approach has its limitations. It can only tell us what we've seen, a pattern we've seen. It can only allows us to extrapolate among known regions. And so having a model, a physical model that can actually guide us through these extrapolations is very important. So we really worked very side to side, let's say, closely with chemists, electrochemists, people that they actually know batteries and know the ins and outs and also the mathematical equations that describe the behavior. And so what we worked with them to use these models and the data and feed the parameters in the model that will tell us if the battery is degrading or not. The uniqueness in my group is that we're trying to estimate or detect degradation and understand degradation, not just the cell lumped capacity and cell resistance like most of us do. And frankly, we hope to do. Even that is hard. But in my lab, we try to actually understand the capacity of the anode and the cathode, and ideally the resistance that occurs because of anode reactions and cathode reactions. We believe that is important to resolve as our batteries age, because that's what is going to give us a lot more information regarding degradation that could lead to failure and could lead to eventually safety issues. And that's why we are kind of drilling right now the last, let's say, 2-3 years into this hard problem on really understanding, is the aging happening and the capacity fade because there are some reactions in the anode or there are some losses, irreversible phenomena in the cathode. The difference between these two can inform us not only about safety and faults and the risks, but also can inform the battery management system that, remember, that's what I do. If the battery management system knows if the anode or the cathode is the one that is degrading faster, then we can adjust on the fly the battery management system to not stress the part that is actually already aging and is stressing. So slow down the stressors and slow down the degradation. Maybe we can derate the battery so that we can safely continue it, not as strong, use it as strongly as before, but less, be gentle, let's say, as they age.
Thank you. That's very interesting. That's great. In field use, although it is very rare, sometimes battery systems don't just age, but they fail due to, for example, manufacturing defects or misuse in the field. And these failures can, in the worst case, lead to a catastrophic thermal runaway and fire. So Anna, your group is also working on methods for fault detection and mitigation for lithium-ion batteries. So could you tell us about that work and how a fault in a battery cell could be detected before a catastrophic failure takes place?
Yes, thank you. Exactly. So, it's an engineered system. Batteries are engineered. They are manufactured and then they're used and abused. And they could fail like all engineering systems. And part of our engineering is to actually understand the risks, have the fault detection, and be able to take actions really quickly depending on the risks if that fault happens. So it's very tricky, like you said, very important to do the detection. So what we have been focusing is we know before a fault, the battery goes into this mode where it generates gases and starts a little, swelling, much more than the general swelling you would see in a general level of degradation. And it swells because of this gas accumulation inside the pouch or the container or the cylinder where the electrode material chemical electrochemistry is happening. So when it accumulates gases, one of the safety system of the battery is to actually vent. So what we are doing is we are doing a diagnostic system that fuses information not only from the voltage of the battery, but also gas sensing, and also we're also measuring the swelling. Sometimes that is hard to measure in a pack, but at least for some applications, we're working on developing cost-effective solutions so that then we can sense the swelling. We can sense the venting. Between venting and thermal runaway, there is a period, and therefore there is a lot to be done in between to, again, reduce or mitigate the risk, or at least make actions to reduce the results of a thermal runaway in a fire or an explosion. This is what we really are trying to avoid. It's the fire, because nearby areas can also contribute to fire, not just the batteries themselves. And of course, explosions and other things that they're dangerous for humans and for property.
Thank you, Anna. So a follow-up question is that can you detect the swelling for the cylindrical cells and maybe prismatic cells with the metal can too? Or is it more for pouch cells?
That's great. Yes, you're right. Absolutely. It's much easier to do that in pouch cells. To measure the swelling in prismatic cells, we have seen swelling. The signal to noise ratio is not that great. It's this metric that gives us high confidence levels, and so we definitely don't want to have false positives very often. And therefore that is still a work to be done, that we're working on developing better understanding for hard encased cells or cylindrical cells. But still the gas sensing, the integration of information with gas sensing, it does work. We have written recent papers and presented some work on sensing CO2 with NDR sensors, which are relatively inexpensive and long-lasting. And that is promising because one can place a sensor in the right place in the pack or in a room, and that is going to be important as we are having big depots with batteries, large recycling facilities, and also large manufacturing facilities. Manufacturing facilities have huge amount of battery storage, and we definitely want to keep these storage areas very, very safe and everything around them.
Thank you, Anna. When a fault is detected, what can be done to prevent the worst outcomes?
Sure, yes. I mean, obvious things is for sure not taking power out of it, increasing the thermal management to the maximum, the cooling, so that we max out, let's say, the cooling when, of course, automated sprinklers, water is really good to immediately activate and cool down the system. Of course, when we know that there has been venting, to also increase the flow rate and the ventilation in the system around that system. Classical techniques, when they detect, by classical meaning like non-battery fires, when we have detection of such fires, we tend to actually seal the area to starve it from oxygen. But here it's not the right, perhaps, way, because we need to ventilate, make sure that we don't have accumulation of these gases that later on can actually cause explosion. And then, there is some time between venting and thermal runaway. And that time, if you have an automated way of detection and quick, as fast as possible, not before it happens, after it happens, like, it vented, these many cells vented. If you know that, you can send in a depot, you can isolate the area with curtains. You can or either air curtains or hardware curtains. You can, again, activate sprinklers, or you can even send you can send a robot that picks up the pack and takes it away from the other packs. And eventually, if we get to that, and I think we will get to that in the technology, can we deactivate and discharge and de-energize the cells around them? So if we have a cell, and we know that this cell or this sector is having troubles, then can we de-energize and deactivate the cells around it so there's no propagation? So one or two cells, they can fail. It's okay. They don't cause big problem, but we don't want the entire pack to start fire, to ignite. So this is what I'm saying, that detection, even when it happens immediately, not even before. I know we want to do it before, but I'm an engineer and I'm going to be realistic. I want to say, let's do it immediately after it happens. And don't lose any time, and act carefully depending on what is the environment and the surrounding property, and also opportunities we have to isolate the faulty battery.
Thank you. Those are very good points. I have one more question. So I was wondering if you could share with us some recommendation on what all of us as battery users can do to make sure that we use our battery-powered devices or EVs in a way that maximizes the lifetime and safety.
As users, I think keep it cool. Not keep it cold, but keep it cool would be something you can do as a user. But I also want to say that as a user, we need to understand batteries and the risks, but also we need to understand that this is it's a growing body of knowledge. And frankly, we will engineer the system so that it is absolutely and totally safe. And even if there are events and failures from the battery side, the actual system will be fail-safe. So I don't think I guess my bottom line and recommendation is like the users should not worry. They should just use their battery-powered devices or EVs, frankly, without fear and without hesitation. And I would say if they are engineers, they can learn much more and dive in and try to understand much more. But even if they're not engineers, really try to understand what a battery is, because it's going to be the future from now on.
So that brings us to the end of this interview. So thank you again, Anna, for joining us and for sharing your work and perspectives.
Thank you. Thank you very much. And I'm glad you're doing this issue, because safety is definitely one of the top concerns, apparently, that has been around. And we know there have been recalls in vehicles. And I think the public should see the recalls as a sign of how thorough we are in engineering batteries and making sure we improve them, we improve the system around them. And from my side as an educator, I want to say that I would, continue working with you and communities that they need to learn how to manage failing batteries, like firefighters and first responders, second responders. I think that's the community that needs to know details and needs to be keep being trained on the new technology and being able to recognize the behavior as it evolves.
Thank you for listening. Let's talk. Please stay tuned for the next episode.